And in a generator, it's important to understand current flows from the positive to the negative. The best way to think about it is a battery. If you just have a standard 12-volt battery, plus to minus, anything external here, any resistor put here, current will flow from plus to minus, right? But what about inside the battery? Which way does it flow? It flows from negative to positive, right? Because that's an ion conduction system, correct, class? It's still, all current flows this way, understand? Inside the actual battery, it flows not from positive to minus, but from minus to plus. Follow me, class? That's because of an ion generator. It's forced to do that. Well, it's the same way. This is actually like a generator. Think of it like the internal of a battery, all right? Current is going to flow in a way such that anything across these terminals will actually experience a current from plus to minus. Understand, everyone? Now do you get it? Now what I'm going to do, if it is like this, and I want to put a voltage in here that would, with the right polarity, so it would have current flow that way, now my actual voltage would look like this, wouldn't it? Where this would be the voltage right here. Follow me? Now the system isn't broken. Remember, this entire thing is like the inside of a battery or a generator. It's forcing current to flow from plus to minus, but flowing in a clockwise direction. All right, class? So when I go to this one, here, I'm just going to show you this. Let me erase this and do it again. I'll just put this here. A1 here is really equal to 0.2 times 0.5. Agreed? And A2 over here is equal, are they the same?
It's 30 centimeters.
This is 30?
Yeah.
It's going to be 0.3 times 0.2, right? So that's 0.1, and that's 0.06, right? That's meters squared, correct, class? Now, if you look at this, I'm just going to look at this one loop right here. If we have, and I'm going to break it so you can actually see this. I'll put a resistor there, but no current can flow. This is 20, or I'll just put this as A1. I know I have the B field coming out of the board, and the B field is over there. It's 10 times 120 pi t milliwebers per meter squared. And I know ds is coming out of the board as well, right? So the dot product of this times this is going to be positive 1 if I think about AX out of the board. Do you all agree with me here? All right. That means when I look at the plus to minus VEMF, according to the law right there, it says VEMF is equal to minus ddt of the integral of B dot ds. What I'm actually going to get is minus ddt of the B field times, or really just B field magnitude times A1. Agree, class? Now, I did that before, but I want you to see it. A1 is a constant, it can come out in front. I take the derivative with respect to t of the B field. That's going to give me this. VEMF is equal to minus A1 times the derivative of the B field, which would be 10 to the minus 2, because it's in milliwebers, so it's 10 times 10 to the minus 3. Then it would be times 120 pi, right? Then it's going to be times cosine of 120 pi t. And that would be in volts. Does everybody agree with me there? This is important. Now here's what I did. This is VEMF, and its VEMF is measured plus to minus here, right? Plus is always going to be on top in a counterclockwise direction. But that minus sign here indicates that these polarities, if we're talking about an actual voltage, I can actually reverse those and make this minus and this plus. Does everybody follow me on that? Now we still haven't completed the circuit. So this would be the voltage right there that would be developed if it was an open circuit. If it was an open circuit. This entire wire here looks like a generator or a battery, think of it that way. Now the minute I put a resistor in here, current would flow counterclockwise, or clockwise, pardon me. Do you agree? So So what I have to do is put a source in there, when I put my actual source, so current can flow, and I have to have the polarity plus to minus. Do y'all follow me on that? Because now the circuit would in fact have current flowing that way. Do y'all follow me, class? All right, so what happens is, we're gonna put a voltage generator right here in loop A1. Just do this with me. And this voltage generator, plus to minus, will have this VEMF here. And that's gonna be, I'll just call it VEMF1. And that's gonna be A1 times all this. Can anybody just give that to me? That's gonna be, A1 is what, 0.1 times 10 to the minus 2 is 10 to the minus 3. So it's 125 times 10 to the minus 3. It's 3.377, is that it? Anyone?
Yeah.
So VEMF1 is 0.377, right? Volts. And what's VEMF2, which would be over here? I'd have to put one in this loop. Right here, say. It would be in the same sense going this way. This would be 1. VEMF2 is the same thing as VEMF1 in a sense, but what? Instead of using 0.1, we use 0.06, correct? So we have 0.06 times 10 to the minus 2 times 120 pi.
0.226.
All right. And it's times the cosine of 120 pi t, right? Now remember, the way I got how to put that polarity in here, I had to see how current would flow if I attached a resistor to the open circuit. And then, based on that, I put my source in there that would cause that to happen. This is if you have a closed circuit. Do y'all follow me, everyone? Now, if that's the case, what is the voltage here gonna be? That's 30 centimeters, or 0.3 meters. Is it plus to minus? Is plus on top?
Yeah.
Probably. How do I get that voltage? Well, what do you always do when you have these problems? Isn't this like let me just make it a circuits problem entirely. You're gonna have to, I've got a resistor here. What's the resistance of this one?
200.
200 ohms? 200 ohms, and I have a voltage plus to minus of 0.33, what? Is it 376? 0.376 volts. We know it's times the cosine. I'll put the cosine in later, all right? We know both are cosine. That's the voltage here. Then I have a resistor here, and what's the resistance on this one?
50 ohms.
50 ohms. And then I have an open circuit, so no current can flow, and I have another voltage here, right? And that voltage is 0.266. Y'all agree? All right, so what is the voltage here going to be? Well, I want you to see this. Current can flow in this loop, right? It's a completed circuit. But no current can flow in this loop, can it? So what I can say is the voltage here, and I'm going to put plus to minus, and I'll just call it V50. V50 can be found by voltage division. Couldn't I just take the total voltage and multiply it by the resistance divided by this resistance and that resistance because they're in series? Do y'all see that? Everybody agree with that? So V50 will be equal to 0.376 times 50 over the sum of 50 plus 200, or 250. And somebody give, that's going to be what? 1/5 of 0.376, whatever that is.
0.0752.
0.0752?
Yes.
52 volts. All right, now what's the voltage here? Well, the way I always, when I teach circuits is, if you want the voltage across an open circuit of any type, start at the negative terminal and go around and see what the net effect is. From here to here, that's a voltage increase, so an increase of 0.226. And then from here to here, right, it's another increase, correct? and it's an increase of 0.0752. And what does that come out to? 0.2952, correct? Right? Is that the answer? It would be times cosine. This would be times the cosine of 120 pi t. Is that what it is?
Didn't see an answer.
There should be an answer down there.
Should be in brackets for that.
It's right at the bottom.
Is it?
What do they have?
301.6.
Then something dimensionally is not right. Just help me out here. This is 5. This is going to be 0.5 meters, right? This is 0.3 meters. And this is 0.2. Agreed?
Yeah.
All right. Well, and this is 200 and this is 50. All right. Well,
The B field is in milli.
yeah, we've got milli there, but what you really, when you're,
But when you solve for V down there, did you do it, you have 10 to the -2.
yeah, but
So
what, 10 times 10 to the minus 3 is 10 to the minus 2, right? Milli is 10 to the minus 3 times 10 is 10 to the minus 2. That's the reason I put 10 to the minus 2 there. And A1 should be 0.1. So 0.1, is this the right value right here? If you have 0.1 times all that? I think it is, isn't it?
Yeah, that's right.
So it's 0.376 about?
When I added the .226 and .0752, I got .3012.
So 0.3012, so the answer, 0.3012 times cosine of 120 pi t. All right, is that right then? Yeah. Agreed, class? Wait a second. Oh, yeah, I see, you're right. Okay, so that's the answer in the solutions manual, and that's how you do it. And it's real important that you hear me now. When you're putting in these equivalent sources, remember, they have to shove current in the direction current would flow if you put a resistor across the open circuit. All right, that's important, what I just told you. Dr. Wentworth's book does not cover this aspect of it. Now, what's that?
I'm just
Yeah. Now, I'm just going to tell you one other thing. See, these kind of problems are things you get thrown at you on the FE exam, the fundamentals of engineering that most of you will take because you want to try, you want to pass that, and then if you're going to be especially working in construction or something like, or building things that FCC or FAA approval, you want to get your professional engineering's license, all right? And that's a thing where you have to take an exam, but they have tons of little questions like that, circuits questions, things like that, that probe and see if you truly do understand the material. Okay. All right. I want to cover that. All righty. Next. That's transformer action, what we're talking about right there, and that's important. But the next thing we talk about is going to be, well, I also gave you some homework that had to do with charge decay and the divergence of J. Did you all look at that and do it? Any questions at all? You understood? All right, that stuff's gonna crop up over and over again. The continuity equation is used all the time. And again, just so you understand where we're at, we presented Maxwell's full equations where curl of H is equal to J plus the partial of D with respect to T. This is called what? This law. Anybody? That's Ampere's law, right? Ampere's law. the other one is Faraday's law of induction. And that's the curl of E is equal to minus dB dt. Now those two we use extensively. We get all sorts of different solutions from them. What is the relationship between the D field and the E field? Do you remember? D is epsilon E, right?
Yeah.
All right, what's the relationship between J and E? Sigma E, right? Keep watching. Well, E could be rendered as D over epsilon, so this could be sigma over epsilon times D as well. And you can say that both J, D, and E are all directly related. They're proportional to each other, and the only difference is the scaling coefficients. Right? That's real important. These you're going to see over and over again. Now, something else I'm going to tell you is that with these laws, these are the differential form. The integral form of this law was that resulted in VEMF equal to minus d dt of the integral of B dot ds, right here over the surface, or minus d dt of the flux, magnetic flux through a surface. This is the integral form of this law right here. Now, this one you used to see like that, curl of H equal J. And then when you integrate and get the integral form, you get the integral, this is for electrostatics, for statics, you get the integral of H dot dl over a closed loop was equal to the I enclosed. That's the I penetrating loop. That was Ampere's law, right? But now because we have this partial of d with respect to t, that also has to be added in here, so it's going to be plus d dt of the integral of d dot ds, and this is really the electric flux flowing through a system. Here's the way you can think about this. This current is real current, conduction current, like flowing through a resistor. This current is like current that flows through a capacitor, which would be displacement current. Do you remember that? No real charge moves from one of the plates to the other through the material, through the dielectric. It's simply electrostatic repulsion or attraction that causes the charge to develop on the plates. Remember that? The capacitor blocks DC. And that means this is the differential real current. That's real charge moving. And this has to do with the displacement current, or flux, electrostatic repulsion or attraction causing the movement of actually the charge on the plates, or infinitesimal changes in the position of charges in the dielectric. Follow me on this, class? This is important. Now, there's one other thing we did with this one right here, and that was to get what? The actual, when I showed you, this is called, some people say it's the fusion equation, but it's really the continuity equation. When we took the divergence of the curl of H, that was equal to 0, and that gave us divergence of J plus the partial with respect to T of rho V equals 0. Do you all remember that? And divergence of D is equal to rho V. And then, furthermore, we took this a step further, and we said if the conductivity was a constant, if sigma is a constant, then I could put J is equal to sigma over epsilon D, and divergence of D is rho V, and I would get sigma over epsilon times rho V plus d dt of rho V equal to 0, and the solution was rho V equals rho V 0, e to the minus t over tau, where tau was epsilon over sigma. Do y'all remember this? Now that's a very common equation right here, these two. And this is the exponential charge decay. The time constant is epsilon over sigma. I just want to make sure I state that again. I did on Friday. Now, the next thing we talk about with respect to these laws is going to be the induced voltage in something moving, just anything moving. And this has to do, you can get it from this law right here. And I'll show you that, but then I'll show you an easier way to do it. So this is a common problem. Please draw this. if you just have two rails separated at a constant distance, so I'll call the spacing here just W, and you wanted to know the induced voltage here between these terminals, top one plus, caused by a bar being moved with velocity V through a B field. And assume everywhere there's going to be a B field coming out of the board. It could be going into the board. Well, if we want to figure that out, I'm going to say this is just going to be some B0 coming out of the board. And I'll give you coordinates. Say X is out of the board, Y in that direction, Z up, okay? Now, you have to assume that this bar is in contact with these rails. It's moving at a constant velocity, and the current can flow, or that at least it forms a closed circuit. Do y'all follow me in this class? All right, now, here's what happens. Y'all see that we have a closed surface right here. You can assume this is a differential gap. It's very small, all right? So I know that the voltage here, VEMF, would be minus ddt of the integral of B dot ds over the surface enclosed, which would be this surface. Agree with me, everyone? Now keep watching, it's important to see this. Well, what is B dot ds? I could go ahead and write a differential surface, right? And then do the integration, correct? Right? But just look at this for a second. The B field and ds are in the same direction. You'll see as the B field's out of the board, the surface vector, ds, would be out of the board necessarily if you take your right hand and just use it to grip the actual surface area. Your thumb points out of the board in the same direction. So I know the dot product of that is already 1. I don't bother myself with that. The B field's a constant, right? So what is S then? Well, S would be W times this distance, right? X of t, correct? And if we assume that this bar starts at this point at 0, right? At t equals 0, assume it's right here, and call that the origin. Then I could say X of t is really just V naught, the velocity, call it V naught here, times t. Do y'all agree with that? If it's moving as 5 meters per second, and it's at 0 at the beginning, 1 second later, it's 5 meters down the thing. It's 5 meters per second times t gives me the position x, right? So the surface would just be W times V naught t. So I have ddt of first the surface, or the area, which is just going to be W times the velocity times t. And then it's got to be times the B field. Now the B field I just said is B naught. It's not time varying. It could be time varying, but it isn't. With me? Now what happens here? When I take the derivative of this, what do I get? Take a look at it. Minus ddt of this. Well, does W vary with t? No. Does V naught vary with t? No. There's a t there. Derivative of t with respect to t is 1. Then we get V naught, right? So really what we have here is minus W V naught B is the voltage. You'll notice it has nothing to do with how far down the actual rails I am. It only has to do with the velocity. Only the velocity and the B field and the width. Do y'all see this, class? And that's it. And it's minus that, which means technically that this would be minus, this would be plus, right? And then I can say that's the VEMF. And if I put a resistor here, current would flow this way. Y'all see that? Okay. Now here's another way to do that same, the same thing. Remember, the B field is not changing in here. If the B field was changing in here, then when we took this derivative, we'd have two parts. We have derivative just with respect to t, t, which gives me 1 times whatever left. But then we have W V naught t times the derivative of b with respect to t, when we have 2 parts to that. And you've got to be careful on that one, on exams. But here's something that I want to show you. If you just have a long bar or a piece of conductor in a magnetic field, it's actually going to be moving through the magnetic field, There's a simple way to get what's the equivalent E field in the voltage. And I'm gonna show you this now. We first start by saying that when we talk about forces, electrical forces, there are electrostatic forces. Remember, F, we talk about F electrostatic just from two charges, like from Q1 and Q2. It's Q1, Q2 over 4 pi epsilon naught r squared 8r 1, 2. That's the force, right? I can also say it's really equal to the charge Q1 times the E field caused by Q2, but it would be the electrostatic E field. That's a force, right? That's the electrostatic force. Now, when you have magnetics, the magnetic force on a charge moving through a magnetic field, it's Q, it's related to Q or Q1, but instead of an electrostatic E field, now we have something called V cross B. Do you remember that? V cross B is a Lorentz force, right? I mean, this isn't actually a Lorentz force. It's called Lorentz force, this whole thing. But the V cross B is like an electric field. It's a force, it's an electric field. Look, Q times that gives me a force. Well, Q times that E field gives me a force. They have the same units. V cross B is volts per meter. So what some people do is they say that this is really Q times the electric field due to the magnetic they do this EMF. So it's the electric field caused by motion through a magnetic field. And really the total force is going to be equal to Q times the electrostatic field plus Q times V cross B, or times the electric field due to the motion through the magnetic field of the charge. This is from the electrostatic charges, really the repulsion, and this is due to motion, and that's important. So what they normally do when they're talking about something of a length L, and it's moving with velocity V. And this is assuming this is a conductor. So it has to be a conductor. And I have a B field here. Some B field that's defined. It could be time varying, it could be electrostatic, it doesn't matter. Then I can say anywhere on this bar, anywhere at all on this bar, I'll get an E field. I'm going to just draw it like this. And that E field will be equal to V cross B. So the velocity of the bar cross B is the E field. Now I'll call this E and just put EMF so you know this is not the electrostatic field. It's due to the motion of the actual conductor in through a charged body, all right? Now if that's the electric field right there, and if I can find out what DL is, so assume DL is a vector, it's a differential vector, then I can say the voltage, really, from voltage across here would be the integral of E, or really of V cross B, dot DL. And technically, this would be minus the integral from A to B would be the voltage VAB. And this right here is usually just E sub EMF or something like that, defining it for the moment. But it's really found by V cross B. Now, the nice thing about what I just showed you is, it's very simple to calculate what this is. If the velocity is this way, and the bar is oriented this way, it's simple to get it. The actual voltage, now, let me just show you one other thing, so you can see this. When I take a look at this, V cross B, if B is out of the board, V cross B, do you see how the electric field would be pointing down this way? That would be E induced or E EMF. Do you all see that? Just take V, take your right hand, use your index finger to be in the direction it's moving, that's the velocity, V cross B. B is out of the board, right? V cross B, E field moving down that way, right? Now that's an induced field. That's like the field internal to a battery or a generator. So which way how is charge gonna pile up? Well, positive will pile there and negative there, right? You follow me? It's forcing that to happen. Understand, class? Okay, you gotta think about that, but that's how you get it. And what would happen if this was cocked at, say, 45 degrees, same length out? What do you think would happen to the value of the voltage between the top and the bottom? In other words, if it's at this angle, where this is now 45. Still moving in this direction. Well, V cross B is still up, isn't it? Right? But the differential is now this way, right? So when we do the dot product, we get what? The cosine of the angle between them, don't we? And we can see that now it's going to be reduced by the cosine of 45, or by 1 over square root of 2. Follow me on this, class? What happens when the bar goes all the way like this to the voltage between the top and the bottom? 0, right? Because then, if you look at V cross B, it's causing, when it looks just like this, V cross B is this way, the E field. We want the voltage between here and here, or between here and here. Well, the DL is in this direction, the dot product is 0. Everybody understand that? These are important concepts. And now I gotta tell you a quick story about this. Does anybody ever hear the name Telstar? It was the first communication satellite we ever put up in orbit, to my knowledge. And when you have a satellite in orbit, everybody thinks a round ball. Well, that's not necessarily the case. A satellite can look like almost anything. That's a satellite. Right? Now, if this thing's moving at a velocity v, right, and there's a B field, and you think about the B field, let's take the B field out of the board. And when I do V cross B, right, I'm gonna get V cross B, I'm gonna get an electric field in this direction. That would be equal to V cross B, and that's the EMF field, right? Now what do you see happening? Positive charge piles up there, negative charge would be left there, right? In space, I want you to think of something. Well, what happens in space, where you're orbiting, you have a plasma. Plasma is an ionized gas that's very conductive. But here's what would happen. The charges would build up there, and there would be this miniature lightning over there, and that means it's actually like heating through a resistor. Current flowing through some plasma. Plasma has a resistance. It's going to cause a heating, and it's going to dissipate power, right? Where's that power coming from? It's coming from the kinetic energy of that orbiting mass. And it keeps on getting reduced and reduced and reduced and reduced until finally it falls to Earth. Well, here's what happened. The people in, this is the story I got at least, that I recall. The people that calculated how long it would take Telstar to come back to Earth only looked at the loss mechanism caused by the collisions with the plasma. Now, you know when an aircraft's going through the air, there's frictional force caused by the air drag, right? If you're going through the water with a boat, the water causes a frictional force. Same with going through this very weak, very, very thin plasma. So they calculate the number of years, and I don't know if it was 50 or 100, some very long length of time, maybe a lot longer. But what they failed to calculate how much energy this is going to be taking, or power this is going to be extracting. And this became the dominant mechanism. So Telstar came tumbling down to Earth unexpectedly very, very early on. As a matter of fact, I think it was about 72 or 74 or 75, 76, somewhere in there. You can look it up. Telstar fell and it landed in Australia. Now, it is an embarrassment to the people that created it. Did you find it? Oh. All right, it's called Telstar. And then they went back and looked at everything that caused that, and they found out that this was the dominant mechanism for energy loss. It wasn't collisions with the plasma. And that changed the way they all thought about things. And I did a paper with a guy named Michael Green, who was a professor years ago, when we actually calculated a lot of the, really the currents that would be induced in tethered objects in space. There's a lot of reason why when you get a main capsule, you're gonna have long pieces of conductor, even if it's not conducting, the plasma around it makes it conducting, long tethers out to different objects that are floating in space for communication work or experiments, stuff like this. And those tethers get a lot of induced current because the orbital velocity, if you're in geosynchronous orbit, I'm trying to think how fast that is. I want to say the escape velocity is on the Earth is 25,000 miles an hour, and that's going to be anywhere from 10 to like 20,000 miles an hour orbital velocities. And that speed, if you do this, the V cross B is very significant. Did you see it?
I'm not finding when it came back to Earth.
Yeah, that's the only part I can't find either.
Look, a satellite lands on Australia. I think you might find it that way. It's an interesting story, but I remember that. Okay. Now, after that, Dr. Wentworth's book has two things. You don't have it in there, but we talked about inductance and things like this. What we haven't talked about is transformers. Let me just hit this. And then we'll get into magnetic forces. All right, I did Maxwell's equations with you. We'll get to time harmonic fields in a second. He does transformers in here somewhere. No. He does transformer action. But let me go ahead and do the transformers now. Have you all had transformers in physics? Do you remember that, or in circuits courses? Did you have transformers?
Very vaguely, I think.
Yeah, very, at the very end.
All right, well, let me go through the basics of this stuff with you. Transformer action is something that we're electrical engineers, it's a component that we use in all sorts of things. Transformers are basically used to step up voltage, increase voltage, or decrease voltage. That's basically it. And if you increase voltage, you decrease current. If you decrease voltage, you increase current for the same amount of power. Now, what a transformer really is a piece of iron core, at least to a high degree of approximation. And assume this thing has some depth like that. And what they do, really, they try to do, they're going to wrap wires around this thing like this. They're going to have end turns. And now I'm going to just go to this drawing. That's try to do the 3D perspective, just the 2D perspective. I'm going to say the core has a cross-sectional area here, A, and it has a permeability mu, and mu is much, much greater than mu naught, which means all the flux is going to be contained in there. And the transformer is going to have current I1 flow there, and it has an N1 is the number of terms on the primary. Now the secondary is going to have plus to minus, well, I'm going to just say this is going to be N2 right here. And we would like to find this voltage, V2. This voltage would be V1. Now that's sort of a transformer in a nutshell. There's N1 terms in the primary, N2 in the secondary. And we have really a magnetic circuit here. Y'all follow me on this, guys? Now I can do this fairly easily. If the cross section is the same, I can say if this is the total length around, I'm just going to call it L, then I can say the magnetic reluctance is just L, right? It's going to be the total length around divided by mu A. That's the magnetic reluctance, right? You're going to have to know how to do this. Now I'm going to build an equivalent circuit for that. Well, I know whenever I have turns, I have some voltage, right? So this is going to be equal to Ni. It's really a magnetic motive force, not electromotive force, right? MMF, right there is Ni, and it's likened to a voltage. This is going to be N1, I1. Then I have a reluctance, and the reluctance is going to be simply R, it's L over mu A, where L is the perimeter, the total length around that iron core. And then, here, since there's no current in the secondary, I have no MMF. I don't have to worry about it. That's my circuit. But what I want to do is find the actual magnetic flux flowing through here. Are you with me? You'll see what I'm up to. All right, well, how do I find that flux? It's just like current. What would it be? Voltage divided by reluctance, that's it. So it's N1 I1 divided by the reluctance. And that's the flux likened to the actual current. Now, that flux is flowing in this circuit. Remember, I didn't hook up any load, right? And when I look at the flux, it flows through each one of those turns, right? Now, when you think about this, well, how much total flux flows through this circuit right here? Well, I could say that if it would be N2 times the actual magnetic flux flowing in one of those, or it would be equal to N2. This is the total magnetic flux flowing in circuit 2. So it's total flux. N2 times the flux, which is going to be N1 I1 divided by the reluctance, magnetic reluctance. Do y'all see that? All right. Now, when I have that, I can, right away, I can get the mutual inductance from this, because if this is the total flux in turns 2, then I can get the mutual inductance would be equal to simply total flux, or N2 N1 I1 divided by reluctance divided by the current causing it, divided by I1. So that means the mutual inductance would be N1 N2 divided by the reluctance, which is the length, total length around the core, L over mu, so then mu would come up here, and then it's times the cross-sectional area A. And that would be the mutual inductance. And then, the next thing, once I have that, did you see this anywhere, by the way, yet? Remember we did magnetic circuits, right? We did this part right here. Now, if we want the voltage, I know that voltage, V1, is equal to really the total flux going through those turns, which is N1. Well, let me do it this way. Anytime I'm dealing with voltage and I'm dealing with turns and current and flux, I always say voltage is equal to minus d dt of really the magnetic flux associated with the turns. This is important. It's a time, you can't have a voltage and a transformer unless there's time varying fields. Transformers don't transform DC. All right, it has to be AC. It has to be a time varying field. So here, when I look at this, the voltage on V1 would be equal to minus d dt of the flux, and the flux, of course, I'm just going to put down, is going to be equal to N times I1 of T divided by the reluctance, called N1. Y'all follow me on this, class? N1 is the number of turns, right? Times I1. Well, N1 I1 divided by the reluctance is the flux, right? And I gotta say this, that's the flux flowing through one turn, correct? So I have to multiply this again because there's N turns by N1. So I get N1 squared times, or divided by the reluctance, times the derivative with respect to T of I1 of T. And to make a long story short, right here, that gives me V1. I'm going to come over here. Let me ask you this. Do you all understand what I'm doing right here? All right, that's just total flux. but the total flux, it's the flux per turn times the number of turns, right? Just the flux is N1 times I1 divided by reluctance. That's the flux flowing through the cross-sectional area. But there's N1 turns, so I have to multiply N1 again. That's where you get the N1 squared there. And that's important. Now, when I look at V2 here, V2 will be equal to, again, now it's going to be N2, because there's N2 turns, minus the time rate of change of the flux flowing through there. And that flux flowing through there is going to be N1 times I1 of T divided by the reluctance. And that means V2 is equal to N1, N2 divided by the reluctance times, let's minus that, times dI1 of T dt. All right, so that's V1. And by the way, you can get rid of that minus sign. I'll show you how to deal with that later. And just make it positive. It's N1, N2 over the reluctance times dy1 dt. Here, V1 is N1 squared over the reluctance times di1 dt. Now, what we really care about is the ratio of V1 to V2. The voltage on the primary over voltage in the secondary. You all see what I'm up to here, class? And what do you see happening? When I take V1 and divide it by V2, right here, do you see how di dt cancels? How the reluctance cancels? And how one of these N1 cancels? And then I simply get the ratio of V1 to V2 is simply N1 to N2. Write that down. For transformers, and these are ideal transformers, it means there's no core, the flux doesn't, there's no fringing field out here or anything. This is going to be a very good iron core, that all the flux is contained within here. And that means the ratio of the voltage on the primary to the secondary can be found by the turns ratio. So if you wanted more voltage in the secondary, if you had 100 turns on the primary, you would have more turns on the secondary, like 1,000. That would be step up of 10, all right? And normally, the we built transformers, but the largest transformer step-up voltage, the largest step-up voltage from a transformer I've dealt with is a neon sign. And that basically the neon sign transformers they take 120 volts and they step it up to 10,000 volts. So that's the turns ratio. We could calculate that. But the thing about transformers is as you increase the voltage, the current is inversely proportional. And what you see is that I1 over, really it's this, it's N1 times I1 is equal to N2 I2. So if you look at that, it means that I1 over I2 are proportional to N2 over N1. It's inversely proportional. And the reason that's the case is, isn't current times voltage power? Well, there's no power loss, so the power going in here has to be the power coming out here, which means V2 I2 is equal to V1 I1. Just keep that in mind. That's the way ideal transformers work. And Dr. Gross will spend a lot of time with this with you. He'll tell you a lot about this. Now, I'll give you some problems on this too. But I wanted to, when you did this problem, by the way, I've noticed all the answers, I think just about all the answers are the same. I don't know, not quite everybody had it. But the whole thing was you work from the gap backwards, right? And the only thing you had to do is put in the given reluctances for each part of that magnetic circuit, and then like do an inverse thing. If you knew in the gap what the B field was, you can multiply by the area. Now you know the current, right? I mean the flux, and that flux is contained within the first section. Anyway, I wanted to do that one at the end of class because that magnetic circuit, it really showcased how just about all aspects of magnetic circuits pretty well. test today or anything? Hmm? In what class?
Linear signals.
How many are in there?
4.
All right. Well, linear signals, now Z transforms, or what are you doing?
Yeah, Fourier's transform stuff like that.
Fourier, okay.
Fourier.
You haven't hit the fun stuff. There's more to come on this. Now, what I'm gonna do is this problem, and give me the specifics on this, because I wanna do this, wanna make sure. I saw some varying answers, but I'm just gonna try to draw this. Well, this is a gross estimate. You've got all these terms here, right? And how many terms?
200,
And we're looking for I, right?
yes.
All right. Then cross-section here,
5 times 10 to the minus 4 meters squared.
cross-section here, I'll call that A1.
2 times 10 to the negative 4 meters squared.
Okay. And this cross-section is the same, I
Yes.
take it? So this is A1, this is A1, okay. Length here,
The
height, whatever you call it.
height is 0.2 meters.
Give me this dimension.
0.2 meters as well.
And this,
0.2.
is that it? All right, for this,
Well,
there's one other thing, is an air gap, right?
yes.
And in that air gap, what do they give you?
It's it's 2 millimeters.
2 millimeters?
2 millimeters.
Yeah, on the right side, it's 0.1.
Is
The
it
length
for
up top.
BECs? What one?
Right here is 0.1?
Yeah.
That's what I thought.
0.1?
Oh, yeah, sorry.
All right. But that's it, right? Now, the way I do this, what do they give you about the gap, by the way? The field,
He gives us
Use
the
the
flux
length.
through the gap.
the magnetic flux. All right, what is it?
I think it's 2 times 10 to the 4th.
Negative 4.
Negative.
2 times 10 to the minus 4th Webers.
Yeah.
All right. Now, that is like a current. Follow me? Magnetic flux is like a current. One thing about current, it's constant in a series circuit, right? I'm going to draw the magnetic equivalent to this right here to make sure everybody sees it. So what we basically have is we have a pseudo voltage, an MMF, that's equal to N times I, and N happens to be 200. Then we have a reluctance. Now listen to me on this one. I'm going to have a reluctance that starts between here and here that is proportional to this length, inversely proportional to the cross-sectional area A1, and inversely proportional to mu. Do you all follow me on this? By the way, what was mu for this one?
UR was 1,000.
So it's, all right, so it's 1,000 mu naught. That means my first reluctance that I put here is just going to be this length, 0.2 or 0.4, plus 0.2, so it's 0.6, right? Divided by, I'll just call it mu, divided by A1, which is 5 times 10 to the minus 4th. And that's the reluctance here. Agreed? Then there's a reluctance from here to here. That reluctance, again, is proportional to length of 0.2, inversely proportional to the cross-sectional area, 2 times 10 to the minus 4th, and inversely proportional to the permeability, or 1,000 mu naught. So here, I take it and I put it down here, and I put in 0.2 over mu, and then it's 2 times 10 to the minus 4th. Does everybody agree with me there? Now, I have a reluctance, not associated with that gap, but this distance minus the gap length. 2 millimeters is so small, I don't care about subtracting that off. I'm just gonna say that's gonna be 0.2 plus 0.1 plus 0.1 or it's gonna be 0.4 in length. Do you agree with me? You can subtract 2 millimeters, but it's not much. So now I'm gonna have a reluctance here that's going to be equal to 0.1, 0.1, 0.2, or 0.4, divided by mu, divided by the cross-sectional area A1, or 5 times 10 to the minus 4th. And then I have my gap, right? And my gap has a reluctance of the length of the gap. This is our gap, and that's 2 millimeters, or 0.002, right? Divided by the cross-sectional area, which is 5 times 10 to the minus 4th, n times mu naught. Agree, class? Now, we know that the flux through here was given as 2 times 10 to the minus 4th Webers. Agreed? That means between here and here, we're gonna have an MMF. I would just call this MMF1, which is equal to this reluctance and this reluctance, and I'm gonna label these. I'll call this R1, I'll call this R2, and I'll call, yeah, that's R gap, and call this R3. So the MMF is gonna be the current, the pseudo-current really, or it's the flux, 2 times 10 to the minus 4th, right? Times R2 plus R gap. And that would be the voltage or the MMF from there to there, correct, class? I'm doing this because I need the current through here, or the flux through there. Gotta get that. Can you tell me basically what this is, a numerical value? I want to work this one. Anybody? If you got it, just tell me. I hope it's right.
955 kiloamps per Weber.
55 times 10 to the third.
Yeah.
And this is
633 times 10 to the third.
10 to the third, and gap?
3.183 times 10 to the 6.
3.10
183.
times 10 to the sixth?
Yes.
Okay. All right. That means, what do I get for MMF? It's going to be R2 plus R gap times 2 times 10 to the minus 4th. I don't know if it's right or not, but you can help me with this one. Go ahead.
763.2 amps.
763.2. And that would be amp turns, right?
Yes.
Amp turns. Now that's like a voltage, right? But we need the current, we need the actual flux flowing here. And I wish I had multicolors here. So I need the flux flowing here, and I'll call it psi 2. So the psi 2, that magnetic flux, would be equal to the MMF 1 divided by the reluctance R3. And that's going to be this MMF divided by R3. Do you have that, this value right here, R3?
Yeah.
Go ahead.
796 times 10 to the third.
All right. And what does this come out to be when I take 763.2 and divide it by 796 times 10 to the third?
It's 9.6 times 10 to the negative 4.
9.6
Yeah.
minus 4th, that would be Webers. All right, now, you see that that flux flows here, there's a flux flowing here, and they will add together, right? That means this flux, I'll call it psi total, put it here, psi total would be equal to the magnetic flux in the middle leg, or call it psi 2 plus the actual original flux, which is 2 times 10 to the minus 4th. And what is the total flux then? Anyone?
11.6 times 10 to the minus 4.
11.6 times 10 to the minus 4th Webers, right? Now, what we need now is the value of Ni, or the voltage causing it, right? The magnetic voltage, think of it that way. Well, here, I'm gonna take the total flux and multiply it by this reluctance, then add it to the MMF there, and that would be the total MMF, because we just calculated that. So that means N times I, or really the MMF total, would be equal to simply the flux, total flux, right here, times reluctance 1, plus the actual MMF1, which is 763.2 amp turns. And this times reluctance 1. So what do you get for this total? Because that's Ni. Right?
1860.
What did you say? 1860?
1860? Yeah.
Something like that.
All right, so 1860 would be N times I, and that means I would be equal to 1860 divided by 200, and I don't know what that is.
9.3.
What is it?
9.3.
Yeah, it's about 9.3, and that's gonna be amps. And if what you told me was correct, that should be right, but the big thing is to see how you really create an electric circuit that's an equivalent to the magnetic circuit and do the problem. You get these things, a lot of people don't get this stuff, and you're gonna see it over and over again. When you get into Gross's class, Dr. Gross, I'm giving you a heads up, he kind of lives in a world of transformers and phases, so you'll see what I'm talking about. Remember, I try to do you justice there. So the next thing we're gonna do in class is gonna go through I'm gonna do the bar magnet lifting power. I'm gonna show you how to calculate how much current times turns. Really, you've seen these big electromagnetics picking up cars and stuff like that in movies and things like that. We're gonna go through how that force is calculated. We're gonna take a look at that. Then, I hope to have time to do this, we're gonna go through the calculations of a railgun and a coil gun. This is something you might enjoy. You'll probably go out and try to make some of these things. But that's really today's lecture, I think. Any other questions? All right, yeah.
In transformers, if everything cancels out except for the number of turns on the first side and the second side, why do you ever use multiple turns on the first side?
No, remember the transformer is the ratio of the primary, which is the first set of turns, to the secondary. So if I put 100 turns on the primary and 1,000 on the secondary, whatever voltage is on the primary, if it's time varying, it will be 1,000 times, or it would be 10 times on the secondary. Why would you put more than 10?
Well, why wouldn't you put, if you're going for 10 times the voltage, why wouldn't you just put one loop on one
That's a
side and
good
10 on
question.
the other?
It has to do with the one turn, there would be a lot of straight flux. But if you put 1,000 turns, then it confines the flux highly to the actual core. There's more to what I'm saying than that, but that's essentially it. It causes a concentration of flux on the core.